Okay, we got to do warm-ups, and we got a lesson to do. So, pass it on, okay? Number one, it says what? F of x is 2x e to the x. How do we know when f is concave up?
F double prime is positive.
We're looking for f double prime, okay? Okay, so what's the derivative of f, first of all?
2 e to the x plus 2x e to the x.
Okay, now we could factor before we find the second derivative. We could factor before we find the second derivative, but it's probably easier just to find the second derivative before we do anything else. So f double prime is what? 2e to the x plus 2e to the x plus 2x e to the x. So we had to use the product rule again, right? Now I'm going to simplify that a little bit. So f double prime of x equals 4e to the x plus 2x e to the x. And then what? Factor. So you get 2e to the x times 2 plus x. If you didn't factor the 2, that's okay. You should still get the same answer. Now, in this case, are there endpoints? Endpoints don't really matter because we're talking about concavity, except for in domain restrictions. But what else are we looking for? Does that ever not exist? No. So we're just looking for when f double prime is 0. So that only happens when x equals -2. Then what do you do? Set up the number line. So you got f double prime is 0 at -2. So we'll plug in like -3 here. What's e to the -3? Positive value. So this is always positive. This is negative. Plug in 0. This is always positive. That is positive, right? So we're looking for when f is concave up. So we're looking for when f double prime is. So our answer is, f is concave up for all x within -2 to infinity, since f double prime of x is greater than 0 over this interval. Just get used to the justifications because they got to be there. Okay? Any questions on that? We good? Number 2, it says when is f increasing, but what did I give you? F prime. So how do you know when f is increasing? When f prime is positive. So f prime of x was x squared minus 2 over x. What is the first critical point that we notice? Why? Because if x is 0, then f prime does not exist, right? Because you're dividing by 0. And then the other critical points is when f prime equals 0. How am I going to solve that equation? Yeah, add the 2 over x. So you get 2 over x equals x squared. Then what? Yeah, cross multiply or multiply by x. So we get 2 equals x cubed. So x equals the cube root of 2. Is it plus or minus? No, because we're cubing a number to get positive 2. So it's got to be plus, right? When is it plus or minus? When it's an even root, right? Okay, so now we've got to do our number line. So obviously 0 is less than the cube root of 2. That's when that's 0. That's when the derivative does not exist. So -1. What do we get if we plug in -1 to f prime? That's positive 1. This is positive, so this is positive. What's a good number there? What's a cube root of 2? What's less than the cube root of 2? 1. That makes sense because if I cube 1, I get 1, not 2. Right? So 1, I get 1 minus 2, so that's negative. What's bigger than the cube root of 2? 2. 2 is good, right? Right? So 2 squared is 4 minus 1, so it's positive. So we would say f is increasing when what? Negative infinity is less than x is less than or equal to 0, and the cube root of 2 is less than or equal to x is less than infinity, since f prime of x is greater than or equal to 0 over this interval.
Would you say over these intervals?
Yes. Thank you, English. Over these intervals. All right. Yes, there were how many warm-ups this week? There was 3, so it's out of 6 there. Okay? I know a lot of you think that I'm being petty on your grading, okay? And you can argue that, and you can think that I'm being petty, but the reality is this is how the AP readers read exams. They are petty too. And you can argue against them, but you can't change their mind. You can disagree with them, but they're the ones that give you the score. And I honestly feel like one of the reasons calculus is so successful here is because I just match the pettiness of the AP readers. All right. So we talked about the idea of optimization, right? Optimizing something is the idea of getting the most out of something, right? Squeezing the last bit of juice out of the lemon, right? So optimization is the idea of taking calculus and figuring out a way to apply it to real life so that we can get the most something out of whatever we're trying to deal with. So we talked about, what was the one example that I gave you yesterday, or a few examples? The one thing we did was the soda can is what we talked about. The fencing, using the least amount of fencing to get the biggest area. Okay? So the idea of calculus is beneficial when you're talking about getting the most money, the most profit, the biggest space, whatever it is. So again, the examples of that are, fencing like we talked about yesterday. And we could have very easily switched the wording around to say what is the least amount of fencing needed to make this much area, right? Okay, and so instead of dealing with the area function, we would have been dealing with the perimeter function, right? Okay. And then the soda can one, so creating containers. And we didn't get to it yesterday, so I do encourage you to listen to the last 5 minutes of 4th period yesterday, because they talked about an example and why a certain shape is more efficient than other shapes. Mm-hmm. Not triangle. Yeah, 4th period. Okay. And so maximizing profit, we talked about that in the election, right? The rate of decline and incline on the poles indicated what was going to happen a little bit. The maximizing a profit when we're talking about stock markets. When is the best time to buy in the stock market? Never. You're looking for when you have a point of inflection where the concavity is changing from negative to positive. Because by the time you make that purchase, it probably hit bottom and you just bought it at the lowest time. And then it goes back up. Okay? The best time to sell is when? Or the best time to observe to make that decision is when it changes concavity from up to down. Because by the time the transaction actually goes through, you're now at the top. Does that make sense? Okay, so that's what all this is about. So again, like yesterday, this all applies in a big way to geometry. So you're going to apply the idea of extrema, f prime. How do you find extrema? Take the derivative and... Yeah, but what are you looking for specifically? Where f prime changes sign. So you're going to find the extrema using that, but using functions that are related to things like area. What else? Perimeter maybe, yeah. What else? Volume. What else? Surface area. Circumference maybe. Well, circumference is going to be a locked-in thing because it's a circle. There's only one variable. It's r, right? Okay, Pythagorean theorem. So again, most of the things lie in the world of geometry. So hopefully you like geometry. I love geometry. Honestly, to me, the two most applicable subjects to real life are geometry and calculus in terms of math. Okay? All right. So let's look at this example. I'm going to give you guys some time to think about this and to work it out. Okay? Find two numbers whose sum is 20 and whose product is as large as possible. So give that a shot. Okay? But that is a good notebook there. The most genius of people do everything on napkins. That is staying on the video. Sam. All right. So the first equation that we're going to say is dealing with the sum, right? So what is sum? Again, addition. So what's the equation we're going to say? A plus B equals 20. Now, we have another equation up there that says whose product is as large as possible. So what are we talking about with product? Multiplication. So what's an equation? Did it tell you what the product is? No. So how many variables are you going to have in this guy? 3. What's the equation going to say? A times B equals P. I'm going to do this. P equals A times B. The reason I'm writing it like that is because I notice the thing that I'm trying to get the largest value of is what? The product. Here, the sum is what? 20. It wouldn't make sense for me to say, what's the largest sum? The largest sum is 20. What's the smallest sum? 20, because it says the sum is 20. So that would be an easy problem. I'm looking for the maximum product, right? Remember from yesterday? Maybe you don't, because we didn't get to it. That's probably why. Okay. In order to solve this, in order to know what the product is, you're going to need to know both of these.
Oh, you have to find the B. Like, if you gotta separate the A, like the B by itself, and then plug that into the other one.
Okay, what are you trying to accomplish by that?
Having A's as your
Just having A's or just B's. Why is that important? We're trying to maximize this. We are trying to find the absolute maximum. Again, how do you find absolute maximum? You deal with derivative, right? Well, P is our function. What's our variable? A and B. We can't take a derivative with A and B as variables because we can only take the derivative in respect to A or B, not both. So we have to get one variable in there. So what are we going to do here? Okay, whatever you want to do. I'll subtract B. What do I get? 20 minus B. Okay. And then we'll take that and plug it in here. So we end up with P equals 20 minus B times B. And then we can simplify that. Now P, the product, is in terms of what? B. So now we have a function. We could say P of B equals, and then you could say 20B minus B squared. So that's our function that we're dealing with now. What are we trying to do with the product? Find the maximum. So go for it. Find the maximum of that product. Now you can hopefully do this. Okay, so working through this, okay? Is there a domain restriction to this problem?
No. Well, I mean, your is like 20. Actually,
Well, wait a minute. Can B be negative or A be negative? Why couldn't it be negative yesterday in the problem? We were talking about area and perimeter, so we were talking about length. And in geometry, length can't be negative. But is there any context to this problem? No. So can A be any value? Sure. So there's no domain restriction here. So what do I have to do now? So P prime of B is equal to 20 minus 2B. And if you put it in terms of A, it'd be the same thing. Okay. Factor out of 2, sure. So you get 10 minus B. So B equals... Is there any other critical points? No, because... Derivative. So there's no other critical points because P prime exists everywhere. So we're going to set up our number line. The derivative is 0 at 10. So let's pick a number to the left, 5. So what is P prime at 5? And pick another number over here. 11. So you get negative. So what can we say about this point? It's not just a relative, it's an absolute, but what's the justification for that? Okay, so
Negative infinity to 10 is strictly positive, and 10 to infinity is strictly negative, therefore it is not.
okay, so your justification works, your vocabulary is not good. Your vocabulary is good, but your justification doesn't work. Okay, he said because P prime changes from positive to negative. That justifies relative maximums. But we're talking about absolute maximum. Okay, just like I told you the other day, this is a relative maximum. Does it mean that it's absolute maximum? No, because there are points that are higher than it. So, using that justification, we would say P prime is positive for every value from negative infinity to 10, and P prime is negative for every value from 10 to infinity. Therefore, it's an absolute maximum. So, we would say the absolute max occurs when, what? B equals 10? All right, and then just the justification I just said. So what am I going to do? What's the question? It says find the two numbers. So we found one of them. Yeah, that one over there, it said A. So A equals 20 minus 10. So it's A. 10, right? So what are we saying? The two numbers are 10 and 10. What would the product be? 100. That's interesting. Why? Do you think there's a relationship between those two numbers and the maximum? Why are they the same? Maybe. Think of what we did yesterday. What shape would optimize the area if it was a rectangle? A square. A square. Okay. No, we're not talking about in the context of this problem, but if we're talking about area, then maybe. Okay, I'm going to give you a set of a process for this that will help you out, okay? So, I guess real fast, just repeating it. The sum is A plus B equals 20. The product is A times B. We're trying to optimize P, the product, so we need to take the derivative of P, so we have to get it in terms of one variable. So we're going to solve for one variable in the sum and plug it into the other one. And then take the derivative and do all that stuff, right? Same thing we just did. All right, I don't want to wait forever. Okay. Okay, I want you to write this next frame down, though, okay? These are good practices with optimization. You can be thankful or not. Last year had Khan Academy. There was a skill on Khan Academy that was brutal. It was the optimization skill. And it's not in their list of things anymore. It's hidden in the calculus curriculum, but it's not on the list in terms of being 100% mastered because it was brutal, right, Gil? That optimization? Oh, Gil didn't do Khan Academy, that's right. Okay. But in order to be successful in optimization problems, you need to follow these 5 steps, okay? The first one is draw a picture if there's a picture to be drawn. In the previous problem, there's no picture to be drawn. But if I'm asking you to optimize area, you're going to draw a what?
Square.
Whatever shape is that we're trying to optimize, right? So maybe a triangle, a square, something, okay? The second thing you need to do is create any equations. That's why we created A plus B equals 20 and product equals A times B. So what kind of equations would you be writing maybe for a triangle? The area of a triangle? Yeah. But what else? What other equation deals with a triangle? How about a right triangle? What? Pythagorean theorem, right? If it's a right triangle. So any equation that you can see. Does anybody know like the volume of a cone?
Why was I
Nope.
Still.
Isn't it 1/2? It's 2. Is E pi?
Nope. Volume of a cone is 1/3 pi r squared times the height. Okay? Yeah, I know it. Okay. So here's another critical part to this, okay? You've got your equations, whatever they are. You have to ask yourself when you're doing these problems, what equation am I trying to optimize? So if I had a right triangle and I said, what is the maximum, what is the absolute greatest area that this triangle could have, which function are we trying to optimize? area. So you would be working with the area formula to take the derivative. If you're trying to find the maximum perimeter, you'd be using whatever the perimeter formula is. If you're trying to find the maximum length of a right triangle, you might be trying to use the Pythagorean theorem. So you just have to ask yourself that and determine what function is being optimized. You can. Yeah. But you have to be careful because most of the time you need two equations so you can get rid of one of the variables. Okay? Fourth step. Okay? Write the function in terms of what? A single variable. That's what we did here. We got this in terms of just b instead of a and b. Okay? And then after that, what did we do? After we have the function, we took the derivative to find the extrema. Okay? And that's step 5. You guys got that? No. Okay. Let's give this a shot. Okay. What is the largest possible area of a right triangle whose hypotenuse is 5 centimeters? This is a fun problem. What's the first step? Nope. Very first step. Draw a picture. What are we drawing a picture of? A right triangle. So here's my right triangle. And it said that we have a hypotenuse of 5 centimeters. So the 5 goes there. Now notice, I don't teach the Pythagorean theorem as a squared plus b squared equals c squared because right now it causes confusion. And most geometry teachers don't realize that because they don't teach calculus. If you are trying to optimize the area, what's the equation for area? 1/2 base times height. So if you're trying to use A, B, and C as your side lengths of a right triangle for a hypotenuse, that's not going to translate well to the area function. What is the other equation that I can say here? Yeah, we're going to use the b squared plus h squared equals 5 squared. Now, what was the next step in our process? We drew the picture. We wrote down any equation we could say. What are we trying to optimize? Are we trying to optimize area or a side length for the Pythagorean theorem?
Area.
So we have to figure out, next step, get a single variable. Right now, area has b and h in it. So what do we want to do? We want to get rid of the h or get rid of the b, right? So we're going to solve for one of those in the other equation. Well, let's see what we do. What did I do? I think I solved for h. I did solve for h. So area in respect to b is 1/2 b times whatever h is. So h is going to be the square root of 25 minus b squared. And if you solve for the other one, it should work out the same. Yeah, it's just switched. So we're going to plug that in. So that is now our function. And we need to optimize that. How do I optimize that? Take the derivative. That's why I told you need to know how to take derivatives. Right? How could you rewrite that so that it's more or simpler to take the derivative? To the 1/2. So it'd be 1/2 b times 25 minus b squared to the 1/2. And now what do you do to take the derivative? Yes, what do you do to take the product rule and chain rule? So what's the derivative of the first thing? 1/2 times plus what's the derivative of the second thing? To the negative 1/2 times negative 2b times 1/2 b. Are you guys okay with that? What do I do now? You can't really distribute because you got the exponents here. These twos reduce, and you've got b squareds, or b times b is b squared. So watch what I do here. This might help it out a little bit. This becomes the square root of 25 minus b squared over 2, right? This is going to be minus b squared on top over 2 square root of 25 minus b squared. You guys see that? You could find a common denominator at this point, but let's find any critical points. Do we know any of them? B, what's the least that b can be? What is the smallest value in that triangle? What was the smallest value that b could possibly be? 0. So critical points are when b equals 0. What's the biggest that b could be? 5, because it can't be bigger than the hypotenuse, right? Hypotenuse is the biggest side. And then we're going to have one more critical point, and that is when, well, is there any time where this does not exist? Negative 5 and 5, right? But 5 we already counted, and negative 5 is outside the domain anyways, right? Okay. And then you solve it from there.
So in order to find that last critical point, we have to look at that derivative and find out when, like I just said, you have to figure out when that derivative does not exist, which we already determined that those points are outside the domain, or we have to set that derivative, which we just figured out, equal to 0. So again, our first two critical points are the endpoints. The smallest value of b is 0 and the biggest value of b is 5. The other critical point is when the derivative is equal to 0. So we set that function equal to 0 and then solve for b from there. Now there's a couple different ways that you can do that. You could find a common denominator and then go through all of that. I think it would probably be best or easiest to add the fraction that we have to the other side. So if you add b squared all over 2 rad 25 minus b squared to the other side, and then cross multiply from there, you're going to find that that radical disappears nice and easily. Okay, so what would you end up with there? You'd get, let's see, b squared equals 25 minus b squared ultimately, and then you can add the b squared, you end up with 2b squared. 2b squared equals 25, divide by 2, so you get 25 over 2, and then you're going to square root that. So you end up with the square root of 25 over 2, which turns into 5 over rad 2, and you can simplify that radical if you want, but notice the question. It says, what is the largest possible area? So now that we have our critical points here, whether we simplify that or not, we have to figure out if that's going to be a maximum or a minimum. So we're going to set up our number line with our 3 critical points, knowing that 0 and 5 are the endpoints, and then the 5 over rad 2 is somewhere between there. In fact, right in the middle of those two. We know the derivative is equal to 0 at 5 over rad 2, and then the other points are endpoints. We have to figure out the signs in between each one of those intervals. So we have to think what might be a good value to plug in. So 1, well, is 1 less than or greater than 5 over rad 2? 1 would be less than, so we can plug in 1 to find the sign between 0 and 5 over rad 2. When we plug that in, we're going to find out that that's actually a positive sign. And then we're going to pick a number that's greater than 5 over rad 2, so something like 4. Again, we're going to plug those values in, the 1 and the 4, into our a prime function here. So that would say 25 minus 1 squared here, and 25 minus 1 squared there, and then 1 squared there, and simplify that. So the sign in between 0 and 5 over rad 2 is positive, and then picking a 4 maybe to go there, plug 4 into all these b values. Plugging in 4, you're going to end up with a negative value between 5 over rad 2 and 5. So that tells us, since this is a closed interval here, that when b equals 0, you're going to have a minimum area, and when b equals 5, you're also going to have a minimum area. In fact, that just makes sense. If b is 0, then we have an area of 0, and if b is 5, then we have an area of 0 also, because if b is 5, then h would be 0, because the base here would match the length of the hypotenuse. So those are both minimum values. That tells us that our absolute maximum area occurs when b equals 5 over rad 2. And then we can plug that into our area formula. After we plug into the Pythagorean theorem to find the other side. But if you plug in that critical point of 5 over rad 2 to our b value here and simplify this, 5 over rad 2 squared becomes 25 over 2. 25 minus 25 over 25 minus 25 over 2 becomes 25 over 2, and we square root it, we end up with the same value, 5 over rad 2. So we notice in this case that b and h are the same values, and then we can take both of those values and plug it into our area formula. And so we'd say 1/2 5 over rad 2 times 5 over rad 2. That becomes 1/2 times 25 over 2, which simplifies to 25 over 4. So our maximum area is 25 over 4, and then the units in this case would be centimeters squared. The second part of this question, it says, what are the dimensions? Well, we just kind of answered that. The dimensions would be 5 over rad 2 and 5 over rad 2. So just like we've talked about in previous examples, it's unique, it's important to note that the maximum area occurs when the two legs of a right triangle are equal to each other. And when we're talking about just basic optimization problems, that's always going to be the case. And that should be something that sparks your interest. It's a very interesting concept to know that the maximum area is when you have a square, or the maximum area is when you have a right isosceles triangle, or more specifically a 45-45-90 triangle if you think back to your geometry. So that's the end of that. I hope this helped you out.